So you can try this problem. This is another problem. You are able to see this slide? Hello?
Yes, sir.
Are you able to see this slide?
Yes, sir.
Okay. Please try this problem. This is a small integer programming problem. Maximize z equal to 4x1 plus x2, subject to 2x1 plus x2 less than or equal to 9, x1 plus 2x2 less than or equal to 11, and the variables x1, x2 are integers like 0, 1, 2, 3, etc. So this problem will solve using simplex method. If you find the solution is integer, nothing to do. If it is non-integer, so we'll formulate some cutting plane, and that cutting plane will help us to find the non-integer solution to integer solution.
So you're not audible. So you're muted.
Now it is okay?
Yes, sir.
But why? Okay, maybe this is, maybe I have to hide. You are the only student in the class, or more are there?
Yes, so there are 20 plus students in class.
How many?
More than 20. I can't see the exact number.
More than 20. I will request you, all the students, you please try this problem. Okay. And in case there is a problem, you are unable to understand, please tell me. So raise your voice so that I will do the needful. There is two in equation. We include slug variables. Slug variables can be x3, x4 or s1, s2. So x3, x4 you can make a slug variable or s1, s2. Then after including the slug variable, present the condensed form of the simplex table. This is the condensed form of the simplex table. We have two basic variables s1, s2, two non-basic variables x1, x2, and one column for the value of the basic variable xb. S1 equal to 9 here, S2 equal to 11, and the value of the objective function equal to 0. With respect to objective function, you can see here zj minus cj, one is minus 4, another is minus 1. Okay, the most negative element is minus 4. With respect to minus 4, x1 is the entering variables. Now we have to find the departing variable. If x1 is the entering variable, departing variable in this manner: 9 by 2, 4.5, 11 by 1 is 11, 4.5 is the minimum among 11 and 4.5. So with respect to 2, we are finding the ratio is minimum. So this 2 is your key element or pivoting element. So in the next table, so you can see here the x1 is the entering variable, s1 is the departing variable. So x1 will come to this position and change the position here. S1 will go to the x1 position, and the table, other things, using the simplex rule we can fill up. So the next table is like this: s1, x1, and 2 is becoming half reciprocal. This 2 you divide by all the elements, half, and this is 1 by 2, 9 by 2. In the same column, 2 is becoming half, and other elements divide by 2 with a minus sign, minus half, and then is 4 by 2, that is 2. And other elements, we apply the PQRS method to find. So in this position, 4 minus 1, that is 3 by 2. In this position, then it is 22 minus 9, 13, 13 by 2. And this will be, so 36 by 2, 18. So the value is like this here. You can see this basic variables are x1, s2. Non-basic variables are s1, x2. In the top, you can put also the cost coefficients, s1 0, x2 something like 1, and the cost coefficients I'm not writing. So presently this solution is optimal. However, the variables are non-integers. X1 is a variable, value is 9 by 2, non-integer. S2 another variable, slack variable, the value is non-integer 13 by 2. So we have to find a cutting plane with respect to the largest fractional part. X1 9 by 2, fractional part is half. S2 13 by 2, here also the fractional part half. So you consider the first one, let us say, you can consider the second one, no problem. Okay, so with respect to this, we have here, so largest fractional part is half. So x1 is selected for the fractional cut. So with respect to x1, we have here x1 plus half h1 plus half x2 equal to 9 by 2, equal to 9 by 2. So with respect to this, our cutting plane will be, you can see here, so half h1 plus half x2, that is greater than or equal to half. And you can simplify also. So if I'm simply adding here, so you can see, or adding or subtracting, so you can find the cutting plane. And if you add, what is happening? X1 plus h1 plus x2, okay, x1 plus x2 plus s1, this is greater than or equal to 9 by 2 plus half, 10 by 2 is 5. And if you subtract, what will happen to this? So that is x1 less than or equal to 9 by 2 minus half, that is 8 by 2, 4. Okay, so both are the cutting plane. You can use the first one or second one. So this, we are using the first one, let us say here, minus half h1 minus half x2, that is less than or equal to minus half, right hand side is negative. So we introduce another slack variable called s3, minus half s1 minus half x2 plus s3 equal to minus half. And once you have established a cutting plane, this to be included in the previous table. Here, how to include? So we have to include one more s2, so one more slack variable. So we have to make some space for another basic variable, the s3, in this manner. You can see here. So first row there is no change, second row no change, third row. So we have put the s3 minus half h1 minus half x2, that is equal to minus half. So according to the rule, this primal simplex method cannot find the optimal solution. You have to use the dual simplex method. In the basic variable column, xb 9 by 2, 13 by 2 minus half. One of them is negative. It looks like the problem is infeasible, not infeasible. So infeasibility, so the primal infeasible, dual feasible. So here you can say this due to the minus half, we have to go for the dual simplex procedure. So minus half, since minus half is there, so it is clear that this S3 will depart. Then which one will enter, whether S1 or X2? That we have to find out. 2 divided by minus half, its absolute value. 2 divided by minus half, its absolute value is 4. 1 divided by minus half, its absolute value, that is 2. 4 and 2, minimum ratio is 2. 2 is coming with respect to the second element. So that is with respect to minus half. That is the key element. Okay. So if this is the key element, what we should do with respect to key element, the next simplex table, we'll take the reciprocal. Minus half reciprocal is 2 minus 2, and the same thing will divide. If you divide, this is 1, and this is, of course, already first instant we have done, it is minus 2, and this is 1. Okay, you can see here 1 minus 2 1, and other rule, you know, in the same column, the same row, this is the outcome. In same column, half divided by minus half with a minus sign. So this is becoming 1. 3 by 2 divided by minus half. Okay, with a minus sign. And then it is becoming 3. And this half, 1 minus half. Okay, if you are taking this is becoming 2. So as a result, we are finding 1, 3, minus 2, 2. And similarly, other element you can fill up. So if you fill, you find here x1 equal to 4, x2 equal to 5, x2 equal to 1, and this, you know, this is 1, 2, and that is the last one is 17. For non-integer case, optimal solution was, you can see here, 2, 1, 18. x1 is 9 by 2, x2 equal to 13 by 2. Non-integer case. But once you are considering integer, and it is a maximization type problem, the value is decreasing. Okay, this is coming 17. 18, it is coming 17. Okay, so we got the answer, and this problem has no alternate optimal solution. Okay, because if there is alternate optimal solution, then in the indicator row elements 1, 2, one of them is 0, then it is possible. Okay, to conclude. So all these 3 basic variables are integer. X1 is integer, that is 4, x2 equal to 5, x2 equal to 1, and our z, that is optimal value, is 17. Any confusion anywhere? Anybody? Any confusion? Have you taken your tiffin? Yes or no? Is there any problem? Not audible? Is it audible or not audible?
Sir, you are audible, sir.
Audible. अरे कुछ तो बोलो.
Yes, sir,
And
you are audible, sir.
You are second year student, not first year. And I heard ragging is going on, so you are busy on ragging. Is it so? Not coming to the class? Some students are saying we are busy with the other activity. President
Sir,
is giving some work.
many students have NSO classes, sir.
But you are not telling so? NSS class certainly not in the evening, say up to 6:30. Which class is up to 6:30? What
Sir,
are the times?
NSO, sports and activities, 6:30 to 7:30.
6:30.
Yes,
and
sir.
after 6:30 any class?
Sir, 6:30 to 7:30.
No, okay. See, this is I am taking extra class because I have taken your permission. But nobody has told me, sir, I have class. So I will stop here, no problem. Okay. So should I stop or I should continue? Because somebody will say that, sir, I have class, I could not attend. Even that NSS class, even some students are not going. Are they going? I don't think that they are going. They take care of their own work, so they don't bother about the class. Okay. Okay, all right, no problem. So this, since you have come, let us continue. Okay. So if you say that, sir, you stop here, I will stop. Okay. We are solving only problem. Is it okay? Next problem. You have pen and paper? Yes or no? Batao?
Yes, sir, we have pen and paper.
Then where is the problem? Okay, try the second problem. Okay, just wait for 1 minute. The second problem, we like to maximize z equal to 6x1 plus x2, 3x1 subject to 3x1 plus x2 less than equal to 20, x1 plus 3x2 less than equal to 25, and x1 and x2 are integers 0, 1, 2. They're non-negative integers, including 0, 1, 2, 3, etc. Okay, so for this problem, can you guess the solution? What is the maximum value? Without solving, can you guess? Your guess is correct. Tell me, what should be the correct answer? Okay.
Sir, 38.
38 is the correct answer. So what is the value of x1?
6.
x1 equals 6, x2?
2.
Yes, it is 38. So, okay. Okay. So, in this problem, what exactly we do? We include slack variables. Then we apply primal simplex method. If in case you find minimization type problem or two-phase simplex method, you can use bigger method. But here, so to make the case very simple, we have taken maximization type problem. Okay, this. So S1, S2 are slack variable. You can mention also X3 and X4 are also these slack variables. The slack variables are non-negative. So this is the initial simplex table, and we are considering the condensed one, not the extended one. Okay, condensed, a smaller table, not a bigger table. So the basic variables are S1, S2. Non-basic variables are X1, X3. So the first row, S1 plus 3x1 plus x2 equal to 20. Then S2 plus x1 plus 3x2 equal to 25. Okay. And we have indicator row elements -6 and -1. So -6 is the most negative. So you take the positive ratio 20 by 3. Then it is 6 and 2/3. Then 25 by 1, the 25 minimum is 20 by 3. So minimum ratio. So 3 is becoming the key element. So with respect to the key element, we have here 3 reciprocal 1/3. Then you divide by 3, 1/3 and 20 by 3. And in the column, you divide by 3 with a minus sign, minus 1 by 3, and this will be 2. And other elements using PQRS method. Okay, this you can see here. This is the table. Now, and this is also optimal. Optimal means all the indicator row elements are positive. Optimal solution, what is x1? 20 by 3. It is not integer, non-integer. Then S2 also non-integer, 55 by 3. 20 by 3, fractional part is 2/3. 55 by 3, fractional part is 1/3. So, which is largest fractional part, that is selected. So, x1 is selected because it has largest fractional part. So, with respect to x1, we have x1 plus 1/3 h1 plus 1/3 x2 equal to 20 by 3. So, with respect to this, we will have a fractional cut in this manner. So, the cutting plane 1/3 h1 plus 1/3 x2, this is greater than or equal to 2/3. So, what is the equivalent cutting plane? If you want to express, you subtract. If you subtract, what is happening to this? This is got cancelled. X1, okay, is less than or equal to 20 by 3 minus 2/3, 18 by 3, that will be less than or equal to 6. X1 less than or equal to 6. So somebody has guessed x1 equal to 6. So we have got from here itself x1 less than or equal to 6. That is the cutting plane. Okay, this will help us to find the solution. This is the first cutting plane. So we may need the second one also. That depends on the problem. So this equivalent one we have got. So this constraint is included in the new simplex table. See, for some problem, this become ulta. Okay, can you read it? But I have merged all the files. Suddenly I cannot. Okay, you can just try. And this I am adding, and after that one iteration. Okay, can you read it? But you have to do some exercise here. Okay, this slide I will give to you because long back I tried it. This file was there. I thought better to show them. Okay, is all right? I will request everybody at least half dozen problem you should solve yourself. Okay, then you will get some experience and get some exposure so that you can solve other problem. Okay, please try. Anybody is solving the problem or only watching? It is not movie that you will watch and something. You have completed this problem? Hello? Anybody?
Yes, sir.
Okay. See, when you have a phone, you have a lot of problem. If I'll switch off, then you have more problem. Okay, they will search everywhere. There is a landline phone. Landline phone, I cannot stop it. So two landline phones are there. So the phone is really, really problematic. Okay, and if you keep, there is problem. If you don't keep, there is problem. Okay, so this is our. So let me see. We like to know one more problem. Okay, see here. See, I have followed a pattern here. You can see 8x1 plus 2x2, 4x1 plus x2 less than or equal to 41, x1 plus 4x2 less than or equal to 46. So 4x1 plus x2 less than or equal to 41. If you multiply both sides, what will happen? 8x1 plus 2x2.
Yes, sir.
So something like it is coming as 82. So somebody can guess, yes, maybe 82 is the answer. But if it is 82, then what is the x1 and x2? So let me know from the problem. What is the answer here? X1 equal to 10 and x2 equal to 1. Okay. So without solving, one can guess also this type of problem. Okay. Right. But guessing sometimes also without working, guessing is also dangerous. Okay. That you have to realize. Okay. So this problem, and one more thing, formulating integer programming problems. So the linear programming problem is natural. Integer programming problems are not natural. It is man-made problem. We are formulating some integer programming problem, but randomly if you take a problem, the solution may not be integer. Okay, so here we have to formulate. So we have formulated such test examples. So this problem, if you are solving, so same way we are considering two variables, two constants. So this is the first table, initial simplex table, and we are using the content simplex table. So with respect to this, you can see here, -8 is the most negative with respect to the most -8. X1 is the entering variable and S1 is the departing variable. Why? 41 by 4, this 10.25, and 46 by 1, this 46. The 10.25 is the minimum ratio, so the 4 is the key element. Okay, this. So, and as soon as you observe here, this, we find the optimal solution. Now, in this example, if it is a non-integer programming problem, what is the possibility? This problem has solution, optimal solution. Not only optimal solution, but also it has infinite number of optimal solution. Why? Because there is a 0. There is a 0. With respect to 0, we'll have the key elements. The key elements you can find in this manner. 41 by 4 divided by 1 by 4. What is the ratio? 41 by 4 divided by 1 by 4. 41. And 143 by 4 divided by 15 by 4. That is 143 by 15. So that is the minimum. So the 15 by 4 is the key element. Okay. If this is the key element, x1, s2 will go. Okay. S2 will go. And which one will come? S2 will go and x2 will come. S2. This is the non-basic basic variable will go, and x2 the non-basic variable will come. Okay, this. But here that is not the question. The question is we want the integer solution. But if somebody is looking for non-integer solution, then this problem has infinite number of such solution. Okay, this is 0 is the indication. When there is a 0 and iteration is possible, this problem has alternate optimal solution. In general, a linear programming problem has either no solution or unique solution or infinitely many solution. If you have seen two solution, then the convex combination say it is infinite. But for the integer, this may not be the case. For the integers, you cannot have the convex combination. Okay, so what the integer solutions are finite, not infinite. Okay, so how to create x1 is 41/4, and you know the fractional cut is 1/4, and s2 is 143/4. This is fractional cut is 3/4. So s2 is selected, not x1, because this is the s2 has the largest fractional part, that is 3/4. So s2 is selected. So with respect to s2, we have s2 minus 1/4 s1 plus 15/4 x2. This is equal to 143/4. And you can find in this manner 3/4 s1 plus 3/4 x2 greater than or equal to 3/4. This is the fractional cut. Okay, where now this constraint to be included in the optimal table of the previous table, whatever, this is the table. Okay, so one more row you can add and proceed. Okay, so this will be minus 3/4 s1 minus 3/4 x2 plus s3. This is equal to minus 3/4. Okay, this to be included. How will include? Will include in this manner. Once you include in this manner, we check whether so problem is feasible. Suddenly it is not feasible, it is infeasible problem. So once we find there is an indication of infeasibility, because the slug variable cannot be negative, it has to be positive. So we apply the dual simplex method with respect to minus 3/4. S3, the basic variable, will be becoming the non-basic variable. Then which one will be the entering variable? You can see here 0 divided by minus 3/4 absolute value, that is 0, and 2 divided by minus 3/4 its absolute value. Okay, that is something like 8/3. 8/3 0. Okay, minimum ratio is coming 0. So this is this 0 is coming with respect to this key element. Okay, minus 3/4. So we apply the simplex procedure. And how to find simplex procedure? This is the reciprocal. So it's minus 4/3, and you divide, that will be 1, and that is 1. And in the same column, you divide by minus 3 with a minus sign. So we have here 1/3, then 5, then minus 4/3, and it is 0. And other elements you can find in this manner. So as a result, we are finding x1 equal to 10, x2 equal to 1, s2 equal to 32, and I have a class, please. Okay, so we have got here x1 equal to 10, x2 equal to 1, and z equal to 30. That is the z square equal to 82. Okay, so that is the optimal solution. So the cutting plane method is clear, or any difficulty? This is the last slide. See, we have also more problem, and already I have put in the slide form. Please try yourself and check everything is right. Okay, some are repetition already there in this problem sheet, so you can. There are 5 problems, C1, C2 up to C5. C stands for the cutting plane rule I have put here. Okay, there are 5 problems, and in fact there are plenty of problems in my computer, so I don't want to disturb you. So only 5 problems I've given so that you can try all the 5 problems. Okay, right? So then we'll move to branch and bound method. It is okay. Branch and bound. How do branch and how do put bound? Okay. Should we continue branch and bound method? Now I want to know how many students are there available online.
Sir, around 30.
Around 30 only. So means these 30 students will get excellent. Nobody else will get excellent. I'm sure. Because if you learn, then you will earn, then you will achieve. If somebody is not interested, see, they know that. So even a AG engineering student can get 1 crore package. He's not bothering about the study. He wants money. Okay. How to get a good package? That is available. No, that how to get a good package he has learned. So he's not interested to study. Okay. Right. If he's interested, maybe after 10 years, not now. Okay. All right. So this branch and bound method. Okay. We'll discuss about the branch and bound method. Okay. So, you know, this method was developed in 1960 by 2 scientists. See, I have forgotten their name, of course, but you see, after that, many other people have applied to solve such problem. Okay, and the concise form of the branch and bound method we'll discuss. Okay, so the problem can be maximization type, problem can be minimization type, constant can be equality type, constant can be greater than equal type, can be less than equal type, and as you know, decision variables are integers. Actually, it is known as all integer programming problem, all integer. And some problems are known as mixed integer. Only few variables are integer and few variables are not integer. So that we are not discussing, we are discussing all integer. Okay. All integer programming problem. All integer means all the variables x1, x2 up to xn all are integers. Okay, this is a standard model. Now, what we should do? The procedure is like this. Solve the integer programming problem by, if it is 2 variable problem, by graphical method or by simplex method by dropping integer restriction. By dropping integer restriction. Simplex method, see how many simplex methods are there? Who can say, tell me how many are there? Tell me how many simplex methods are there?
So
it is convenient to use primal simplex method as well as dual. Okay, so primal or dual, because now I'm stating these two. When primal, all the constants are less than equal type. When dual, constants are greater than equal type. But now you may say, what about to the equality type constants? How do you include? So whenever there is equality type constants, you can change 2 different in equation. Okay, one is less than equal type, another is greater than equal type. For example, x1 plus x2 equal to 2. So x1 plus x2 less than equal to, and x1 plus x2 greater than equal to their intersection. Okay, so these 2 are included. So now either you use primal simplex or dual simplex, no other. Revise simplex certainly we are not advising. So big M method I am not advising. Either primal simplex or dual simplex. Okay, right? So then what we'll do? Next step. Let xj be an integer variable whose optimal value is xj star, which is fractional. Earlier, see this example say we have taken some problem. Let me say some problem. x2 you can see here, what is x1? x1 equal to 5 by 3. x2 equal to 4 by 3. This x1 and x2 will be integer. We are interested in integer, but presently their value is fractional and this table is optimal, and optimal solution is fractional, not integer. But if it is happen to be integer, then you stop. Otherwise, we'll try to impose some condition. X1 equal to 5 by 3, X2 equal to 4 by 3. Same thing here we are discussing in the branch and bound method. Xj can be X1 or X2 or X3, be an integer variable. It is supposed to be an integer variable, but optimal value we are naming as X star. This X star is fractional. Why fractional? 4 by 3, it is fractional. 4 by 3 means 1 and 1/3. 5 by 3 is also fractional. 1 and 2/3. Okay. So then what is happening? Then this Xj star is fractional, but Xj has to be integer. This Xj less than equal to Xj star plus 1. For example, my Xj star equal to 4 by 3. Xj star equal to 4 by 3. So what is the integral part of 4 by 3?
4.
What is the integral part of 4 by 3?
Sorry, 1.
1. So Xj less than equal to 1 plus 1, 2. And Xj greater than equal to, this is simply greater than 1. So Xj lies between 1 and 2. Xj less than 2 and greater than 1. Xj less than 2 and greater than 1. So here what is say that, can you find an integer which is in this interval? Xj less than 2 and greater than 1. In interval 1 and open interval 1 and 2. Is there any integer?
No,
No.
sir.
So this cannot include any integer solution. This cannot include any integer solution, right? Then which interval will include? So this says, this implies a feasible integral value of Xj must satisfy Xj greater than equal to integral part of Xj star plus 1, less than, not possible. So greater than, or Xj less than or equal to Xj star. So we are taking the complement. The complement says this cannot include. Then which will include? The complement. So Xj greater than equal to Xj star, its integral part plus 1, or Xj less than equal to Xj star is integral part. These two are two different branching, this or that. Okay, this or that. Hence, with respect to particular Xj, will branch two different constant. So this is one constant, this is another constant. Okay, right. So by imposing the constant 2.7 and 2.8, it should be 1.7. Okay, 1.7 and 1.8 to the original LPP, we find two mutually exclusive LP problem. It is not 2.7, it is 1.7 and 1.8. So by imposing constant 2.7, that is 1.7 and 1.8 to the original LPP, we find two mutually exclusive LP problems. Okay, this. Hence, the problem is branched into two subproblems. The optimal value of the objective function z for the non-integer case, it is z star. Now, we are considering a problem, either it is maximization type or minimization type. Now, with respect to this branching, you see here the optimal value. For a particular problem, the optimal value of the objective function we are naming as z star. Okay. Further, hence, the problem is branched into two subproblems. The optimal value of the objective function z for the non-integer case is z star. For the integer case, integer is discrete, the optimal value z star has to be less than or equal to z star its integral part. It is a upper bound to the objective function. Branch and bound. Branching is done. Now bound. We put bound for the objective function. Okay. It has to be So since let us say you are considering a problem, so z star once with respect to z star, once you are considering the integral value, so this is less than equal to z star. Okay, here is integral part. It is a bound, that is upper bound for the objective function. Okay. This procedure is to be repeated a number of times to find an all integer solution x star. Okay. This will explain using some example. The steps are all right? The steps are all right? Or any confusion? Branch and bound. It is a very standard language in optimization, in computer science, in mathematics. Okay, branch and bound. B and B we say. B and B. Branch and bound. Okay. See a problem. This is an example, say here. Maxima is z equal to 5x1 plus 4x2. I think same problem I have solved earlier. 5x1 plus 4x2, x1 plus x2 less than or equal to 3, 4x1 plus x2 less than or equal to 8. This is elementary problem. How to solve this problem? Can you use the graphical method here? Can you use the graphical method? Anybody?
Yes, sir, there are two variables.
Two variables, graphical method is possible. Okay, we will solve it. So in the exam also, for the branch and bound or for the integer programming, so I suggest that okay, only two variable problem will be asked because these are the classroom problems. Okay, so now with respect to this two variable problem, you can see here same problem. You can solve using graphical method or using the in a simplex method. Okay, why graphical method? Because two variables problem quickly. Okay, so if you are using graphical method or the simplex method, you will find solution. Our solution for this example is like this. Solution x1 equal to 5 by 3, x2 equal to 4 by 3, and what sort of solution it is? It is non-integer solution, right? Non-integer solution x1, x2. So we will select one of the variable. Generally, we select the variable which has largest fractional part, 4 by 3, 5 by 3. Okay, so which one will consider? Anyone you can consider, no problem, but which one will consider? Okay, this solution is like this. X1 star equal to 5 by 3. It has largest fractional part 2 by 3, and x2 equal to 4 by 3. It has fractional part 1/3, and z star, as you know, is 41 by 3, but z star is integral value is 13. Okay, this. So we like to know what is the optimal solution. What is the rule here? We have selected x1. Why you have selected x1? Tell me why you have selected x1. It is largest fractional part. Okay. X1 star equal to 5 by 3. So this x1 is less than or equal to integral part of 5 by 3 plus 1 and greater than integral part of 5 by 3. This interval does not include any integral solution of, there is no integral solution in this interval x1 less than 2 and greater than 1. So if this cannot include any integral solution, then which interval will include? So the complement. So here x1 has to be less than or equal to 1. This complement. Greater than or equal to 1. Complement is x1 less than or equal to 1. x1 less than or equal to 2. Its complement greater than or equal to 2. These are two different. x1 less than or equal to 1 and x1 greater than or equal to 2. So here we have initially the problem is P1. This problem is P1. Please remember, this is our problem. Okay, we can say P1. Then we have, this is our P1. P we are saying P1. Now we are branching two problem. Not visible, you can see here. P2 and P3. What is P2? P2, everything is same. We have added this constant extra. What is that? X1 less than equal to 1. What is P3? Same problem. We have imposed this constant X1 greater than equal to 2. You can see everything is same. In the P2 second problem, X1 less than equal to 1 included. So in P3, X1 greater than equal to 2. So two different branches. So P1, graphically it will be something like that. P1, P2, P3, P1, P2, P3, P1, we got solution accordingly like this. So left branch is P2, right is P3. In left branch, X1 less than equal to 1, and right branch, X1 greater than equal to 2. Now two different problems we are solving. So if you solve the first problem, P2, we find solution X1 equal to 1, X2 equal to 2, and Z star equal to 30. P3, so X1 equal to 2, X2 equal to 0. Okay, once you have got integer solution, no need of branching further. Once you got integer solution, no need of branching further. Okay, similarly, P2 and P3, both we got integer. Now, if you compare P2, P3, and the problem is maximization type. Problem is maximization type. Which one will you select? P1 or P2? P2 or P3?
P2.
P2. Okay, so this P2 gives better solution. So this is the optimal solution, not P3, because it is less. But if it is minimization type problem, which is better? P2 or P3? It is
P3.
maximization. For maximization, P2 is better. For minimization, P3 is better, something like that. Okay, so we have got this is the answer. X1 equal to 1, X2 equal to 2, Z star equal to 3. Okay, and graphically it is like this. So you can see here Z2 star greater than equal to Z3. So actually it's a strictly greater. Both can be equal also. Okay, see here no branching is possible because already got integer. If it is non-integer, further branching is possible. Okay, branch, it is binary. Okay, again if you are going to branch, again from P2 we'll have P4, P5. Okay, from P3 we'll have P6, P7, something like that. Okay, to branch accordingly. Second example. Second example. I will request everybody. You should try the second example. Okay. Please write down the problem and do it yourself. I will explain what you are doing. And here you need not do the simplex. You just try with the graphical. 10x1 plus x2, and we have 2x1 plus 5x2 less than or equal to 11. See, if I am setting x2 equal to 0, then we have 2x1 11, x1 equal to 11 by 2, and there we have what? 10 into 11 by 2. 10 into it is coming 55. Okay. 10 into 11 by 2, so it is 55. The objective function value is becoming 55, and x1 equal to 11 by 2, x2 equal to 0. That is giving maximum. Okay, but it is giving maximum, but the solutions are non-integer or integer. Non-integer, x1 equal to 11 by 2, 11 by 2, x2 0, and z1. Okay. Now with respect to 11 by 2, so we'll have branch, two branch. x1 less than or equal to integral part of 11 by 2 plus 1. Okay, that is 5 plus 1, 6. And x1 greater than or equal to integral part of 11 by 2. That is x1 greater than 5. So this interval, if I am saying x1 less than 6 and greater than 5, this interval has no integral solution for x1. Okay, then which interval has the complement? X1 greater than or equal to 6 and x1 less than or equal to 5. And you impose this constraint and solve it. If you impose this constraint and solve it, the problem is not feasible. Left side, you can see here, I'm substituting what x1 less than or equal to, sorry, x1 greater than or equal to 6. X1 greater than or equal to 6. Once you, in this problem, this is our P1 and the P2, another constant you are adding, x1 less than or equal to 6. So problem will be feasible or infeasible? See, here it is giving x1 less than or equal to 11 by, if you say x2 equal to 0, 11 by 2. But then x1 is given greater than or equal to 6. x1 less than or equal to 11. x1 greater than or equal to 6. Are they feasible constants? No. Infeasible. Okay. Less than or equal to 11 by 2 and greater than or equal to 6. Okay. So it is infeasible. This problem is infeasible, not feasible. So once it is infeasible, you drop. No question of finding solution. Now you impose x1 less than or equal to 5. Okay. So once you are imposing this and we have solution. What is the solution here? You can see x1 5, x2 1 by 5 and z2 50 and half. 50 and 1 by 5. Okay. So already x1 is integer. Which is not integer? X2 is not integer, 1 by 5. And what is integral part? 1 by 5, 0. So x2 less than 0 plus 1, 1 and greater than 0. So here we have two mutually exclusive constant here. So x2 greater than or equal to and x2 less than or equal to 0. So negative is not allowed. It can go up to 0. Okay, not anything here. So if you solve, what you are finding? So this constant give x1 equal to 3, x2 equal to 1 and z equal to 31. And the right hand side give x1 equal to 5, x2 equal to 0, z5 equal to 50. 31 and 50. What is the optimal solution? Yes. Optimal solution equal to 50, x1 equal to 5, x2 equal to 0. Right? Next example. Example 3. Will you please try yourself? Try. Example 3. Solve it either graphical or simplex method and take the decision. What is the solution you are expecting? Optimal integral solution? Anybody? See this one, we are solving. So if you solve, okay, any method, so we are getting solution x1 equal to 6, x2 equal to 5 by 2. A similar problem we have solved earlier, okay, and z1, objective function of z equal to 13 by 13 and half. With respect to 5 by 2, we have imposed constraint x2 is less than equal to, okay, then x2 greater than equal to 3. So if you put in this manner here, So we got a solution like you can see x1 equal to 7, x2 equal to 2, and z equal to 13. And if you impose this constraint, we have so x1 equal to 4 and x2 equal to 3, z3 equal to 13. What is your conclusion? What is your conclusion? Both sides 13.
Infinite number of optimal solutions.
No, not infinity. Okay, these two I have given. Give me third solution. With respect to this problem, give me third solution. For the linear programming, the infinity is meaningful. For the integer programming, it's not meaningful. It's discrete, no? How
Okay.
do?
Yes.
Okay.
Sir.
So only two. There may be three. You can find out, but you cannot say infinity. Okay. Right?
Yes, sir. I wasn't thinking in terms of integers.
Okay. That's all. So these two topics are very interesting. You can have more problem. Okay. And we have reference. This book I have told earlier. H.A. Taha. Okay. Operation Research. And Phillips Ravindran Solberg, also another book. Okay. So generally the first book I used for several years, and this is good for the students. Okay. But some part of theory may not be sufficient. So, okay. Any query from this topic? I will stop here because you have not taken tiffin and your dinner time is ready. So you are getting good food in the hostel. Nowadays, it's good quantity of vegetables are available in market and cheaper. Is okay or not okay? You don't like? Only few halls food is good, and some all the halls people complain sometimes good, sometimes not good. But whoever is the mess secretary, you just try to control and plan your menu accordingly so that you will get good food. Okay. I will stop here. Okay. But my request is try to solve problem, learn the subject thoroughly, and if any doubt, you can interact with me. And if there is a confusion, and try to write code or take the help of some software. For example, Mathematica is one software, MATLAB is another one, and few others. Okay, try to learn. Okay, so why software is required? The question is you are solving problem, and you have to check your answer is correct or not. Then this software will help you. Okay, whether answer is correct or wrong. If it is not correct, then you have to know what is the correct mistake you have done. Okay, that's all. You know what are these softwares available to solve this problem? I will not find. I will not tell you, because if I will tell, you will not learn the subject. You will look at this. You have to search for the software. Okay, you try, but certainly MATLAB nobody can hide. Mathematica nobody can hide. Such problems you can such software you can use. Okay, right? Thank you. We'll stop here.
Sir,
Yes.
can you send that handwritten PDF which we are presenting?
Everything I will send, but I am sending where it is going. I am also. Can you do me a favor? Make a group mail ID in Gmail and send to me. Okay. So I will.
Sir, we are getting all the mails from you, so there is no problem.
But somebody said that I have not received anything.
Okay.
Some students are saying. So I think they are not coming to the class, isn't it?
What,
okay.
sir?
Handwritten certainly I will send. Okay.
Yes.
This Taha book you have you collected some book, test book. Some test book you find, see, and the choice of book is yours. You like this language, this style of presentation, you like more theory or more problem, you have to select book. See, I will tell some books you may not like, but Taha is a good book. Okay, it is available. In the tech market, you will find, in the old bookshop you can find. So, okay. And soft copies are also available in online. In online, there are some free book sites, isn't it? You know it? See, if it is available free, you can. But certainly, if you are using some pirated book or pirated software, sometimes it's a problem. But in education, there is no such problem. But you are using only. You are not selling. Okay. Thank you. I will send all the slides. Okay. This today is whatever you discuss.
Thank you,
This is
sir.
already. Yes. Anything? So tomorrow we'll have class also. Okay. Don't miss tomorrow class. Okay. Then after that I will plan for your test, second test. What is the topic I told in the second test? Can you remind me? Integer programming and what else? I have forgotten also. I have to see the mail. Okay. See you tomorrow again 6:30 to 8 o'clock. Okay. Bye.